In the last video, we decomposed the simplest possible self-persistent geometry, defining the simplest possible self-persistent universe. The boundary conditions of this minimal universe precisely define the Planck constants, the bounded limits of the 5 dimensions of our physical reality of time, space, charge, mass, and temperature. In this video, we explore how the 2 external-facing boundaries of that projection, the Planck charge and the Planck mass boundaries, maintain themselves under hyperbolic closed connection, and, therefore, subdivide into very specific expressions geometrically, defining all the charge and mass assignments of the fundamental particles of matter. Then, we discover that the unique balanced intersections of this minimal geometry, this minimal universe, define the constants of nature. Chapter 6. The Hyperbolic Vortex. The hyperbolic figure 8 knot's exterior domain is maintained under self-closed hyperbolic connection. Now, hyperbolic connection is just the trivial hyperbolic form, 1 over x plus x plus x cubed. Okay, this is just the unit hyperbola. I'm using je for my variable instead of x. Okay, but we don't want a hyperbolic connection. We want a self-closed hyperbolic connection. And the difference between those are just this 2 pi on the third component. The first 2 inverse components are unchanged. Those 2 still maintain their inversion. But the third component is wrapped around a circle. That's a self-closed hyperbolic connection. The action responsible for this self-closed hyperbolic connection trivially involves 2 orthogonal twists. It's the simplest thing we can say about it, right, geometrically. Both of which are internal to what? The mass boundary. We can use I to the I as a single twist, a rotation of pi over 2 radians, right? But I to the I is the same thing as e to the negative pi over 2. So if you think of it in e form, it's e rotated negative pi over 2. This is the same thing as I to the I. We could then layer this to have a single twist raised to the negative pi over 2. And this now represents an orthogonal combination of 2 internal twists. Setting these 2 conditions equal to each other yields the hyperbolic vortex equation. Setting this self-closed hyperbolic connection equal to being 2 simple twists internal to the mass boundary. That requirement defines the hyperbolic vortex equation. That equation has 4 solutions composed of 6 parts, 4 real and 2 imaginary. If we plot these solutions in the complex plane, we have je1 very close to 0, but not 0, but it's on the real axis. Its imaginary component is 0. We have je2 also with a 0 imaginary component. But je3 and je4 are both in the negative direction in the real component, but also in opposite directions in the imaginary component and not 0 values. These hyperbolic vortex partition constants are ideally cyclic and combinatorial. For example, their product is equal to 2 pi. They sum to 0, as do their real and imaginary parts. Their squares sum to the projection of a sphere, negative 4 pi, and so on. je1 times je2 times je3 times je4 is equal to 2 pi, a circle. But if we add them instead of multiply them, we get 0. If we add only the real parts of all 4, we get 0. If we add only the imaginary parts of all 4, we get 0. If we square each solution first and then add them, we get negative 4 pi, and so on. In fact, je3 and je4 don't have to be represented in the xy coordinate plane, right? They can also be expressed in terms of radius and angle. So je_r and je_theta have very specific values too. These are geometric parameters, the hyperbolic vortex radius constant and the hyperbolic vortex radian constant. Je_r squared is equal to je3 times je4, and je1, je2, je_r squared is equal to 2 pi. These partition solutions define how the external facing boundaries of the hyperbolic figure-8 knot divide under closed hyperbolic connection. Therefore, they define how the Planck charge and Planck mass boundaries naturally partition. Let's explore those partitions. Before we do, we can sum up the combinatorics of the hyperbolic vortex partition constants in a little cleaner notation in the summation or product notations like this. Now that we know the fundamental division parameters of this hyperbolic arrangement, let's talk about how the external boundaries are arranged. Chapter 7. Charge partitions. Externally, charge has a magnitude equal to the charge boundary, right? The Planck charge boundary, multiplied by the first hyperbolic vortex partition constant. And this defines the charge of the electron to every significant digit, perfectly defines the charge of the electron. Internally, charge partitions exactly as the volume of the hyperbolic figure-8 knot partitions in the imaginary or internal direction into a negative 1/3 and positive 2/3 division. One of the ways you can define the volume of the hyperbolic figure-8 knot is with this mathematical equation where you have a split dilogarithmic flip, and we have a 1/3 parts and a 2/3 parts, and then 1/3 parts negative and the 2/3 parts is positive. So it's a 1/3 part of what? Of a dilogarithmic flip. The flip is the -1 sign in the argument. And this is all in the imaginary or internal direction. This means we have charge arranged very specifically. The external charge boundary is arranged into one specific form. It takes the Planck charge boundary and wraps it by the first solution of the hyperbolic vortex, the throat of the hyperbolic vortex. And internally, that throat, of course, is a throat that wraps around the boundary of the hyperbolic figure-8 knot. So the internal divisions of that arrangement define the division parameters of the internal construction of the hyperbolic figure-8 knot. This single arrangement gives us the beautiful construction of all the possible expressions of charge. The external expressions are either the electron charge or negative the electron charge or zero. But internally, when you look inside of one of those, you will either measure it. There's 3 different ways to measure it. You can measure it as having a value of negative 1/3, -1, or positive 2/3. The scale of charge unity is equal to the electron charge. So what we're saying here in this single page about how charge partitions is that the Planck charge boundary is the only thing of charge in existence. There's only one action making up the thing we're calling charge, okay? And that Planck charge boundary in this minimal balance construction, it externally expresses itself because it's wrapped into this hyperbolic vortex arrangement. It's the part that's wrapped around the throat. It's got the little smallest part there. So it gets the first partition solution of the hyperbolic vortex arrangement. Partitioning what? The Planck charge boundary. So this is the natural partition arrangement available to charge in nature. The prediction of the electron charge's value to begin with, and the geometric explanation of where it comes from, tying to where charge itself comes from to begin with, is priceless here. Absolutely priceless. I mean, think of the level of comprehension that's coming in here. We know the division balance, the actions on each scale that's going on. And each unique boundary of action defines a limit of dimension in this balance, a limiting thing that can be looked at, a limiting thing that's participating in reality. And the boundaries themselves, since they're unique, they have to be given some sort of unique name, and we're going to call them, of course, what the dimensions of reality are. And they numerically select out the values of the Planck constants, which define the limits of the dimensions we've measured in physics. And it selects the exact numeric values of the numbers we most needed to explain. If that doesn't get you excited, I don't know really what will. But get ready for more, because if you're a fan of science, you're well aware that several models have perfectly prescribed the division parameters of unity of charge, right? This prescription of plus and minus ones and zeros and negative thirds and positive two-thirds and so on. That prescription is not so difficult to make a model of. What's never been done in any way whatsoever really is a prediction of what the value of the electron charge is, where this unity comes from. So you don't have a full understanding of it until you understand the geometry of that division. Here, we understand the two-part mystery. What is charge to begin with? If you want to understand what the electron charge is, you need to know what charge is, and then you need to know what arrangement that charge is put under, what geometry it holds, what expression it maintains, so you know what its fixed parameter is. Fantastic. By defining just the boundary of charge and the first division parameter of the hyperbolic vortex arrangement, we select the electron charge, the expression of charge that nature gives us. Chapter 8, Mass Partitions. The mass boundary. This is probably going to be a familiar path now. We're going to explain not the Planck charge boundary this time, but the Planck mass boundary and its geometric arrangement. So the Planck mass boundary has a geometry that trivially binds two figure-8 knot volumes. All right, let's pause there for a second. We're at the last external partition boundary of the hyperbolic figure-8 knot. And the hyperbolic figure-8 knot's a double cover on the inside, and it has a volume that we label with the constant V sub Fe. So externally, that balance, it's got to be balanced externally both ways to counter against this internal double cover. So there's two volumes of the hyperbolic figure-8 knot that are externally traced about, shaping the form of what? The Planck mass boundary? Close. Shaping the form of the mass boundary. But this mass boundary is now composed of 4 Planck mass boundaries. Why? Because it has to trace around the hyperbolic figure-8 knot form, but because it's arranged as a double cover, it needs to go around in a Mobius way, so it has to go around twice each one. So it has to go 4 of these unit boundaries to close the loop. So this minimal external last division expression, we're taking the entire volume now and closing out that whole volume, and we're using 4 boundaries to close this whole thing out. It just smoothly closes. And externally, what's our external arrangement? Wait, let's pause for a second. Before we get to the external part, you have to be in awe for just a little while, don't you, about the simplicity of that geometric solution. We're taking the mass boundary, the one we've defined early as the third balance of the division of the hyperbolic figure-8 knot. So it's one of the external balance projections. And we're wrapping it in the external projection of that knot's wave, right, to close it out. And that alone, if we didn't even mention anything else, that alone selects the mass of the electron to the first, roughly 7 significant digits, or plus or minus whatever the value of inverse hyperbolic sine of inverse hyperbolic sine of 44 over 7 is. That's mind-blowing when you consider all this time, out of every physicist that's been in awe of the construction of our reality, every philosopher and religious person who's reached to try to understand more, nobody's come up with a single story yet that could predict or generate a value that the electron should have to any degree of precision. It couldn't get to the 9.1 times 10 to the negative 31, and then no idea on the rest of the digits. No one's gotten anything at all yet that can predict what the value should be, that would make sense of it being that. And here, the simplest thing that the mass boundary could be defines the mass of the electron. That's a really good start for a system when you're trying to make sense of the world or the constructive parameters of the world. When the dimensions themselves take on the geometric forms of the things you needed to express. Terminally now, this trivially closes in a hyperbolic way, right? Inverse hyperbolic sine of inverse hyperbolic sine of the entire derangements of the system have to close out here. So all of our 44 derangements are now closed, divided by the break and scale symmetry. I like to spend a little bit of time every time I pass this to be in awe of the precision of this measurement, first of all. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant digits, and the error plus or minus 28 is still relatively small. So this number is something we trust quite well, and it represents one of the best achievements we've ever made, right? This is one of the numbers that constructively define to the highest degree of our measurement so far what reality is. But hidden in this number until now was the story of what it meant. It's a number we've known to the greatest precision, and we had no story for what that number was telling us about reality. Here is a simple, beautiful story. This is the first place where we're really pointing out the terminal boundary, which is this box symbol on the far right. This terminal boundary, or termination boundary, is defined as the Planck length times by the Planck mass divided by the Planck charge squared. Or you could think of it as the Planck length divided by the Planck charge. So Planck length compared to Planck charge multiplied by the Planck mass compared to Planck charge. And then both of those multiplied together. It's the split squared intersection of the Planck length, mass, and Planck charge boundaries. Every balance is terminated on this specific termination boundary, on this division line between the internal and external domains. So we have that going for us as a simple constructive rule in our simplest balance. And that constructive rule has a lot of simple things to keep in mind. First of all, it defines this connection as being that which defines the n hypersphere of maximal volume. What do I mean by that? Well, when we take the sum of our 5 rotations, rotation 0 through 4, and add them together, we get the total amount of rotations that all 5 of these things are contributing to this balance. And when we check under this constructive arrangement, under the assumption that there's a balance being maintained between 2 parts, and both of those parts have boundaries and geometric actions that are playing a role on the boundaries to make a balance. It turns out that the internal part ends up taking a sphere and dividing it in 3 ways by the omega-1 constant, the equiharmonic half period from chapter 4. And it has another division parameter, 2/3, which we remember, but this time it's squared. Externally, though, the division parameter is 3/2 squared, so the intersection between the two goes away. And the value of the dimension at which the n hypersphere has maximal volume. It singles out very specifically the dimensional value at which the n hypersphere has maximal volume, and it divides that dimensional value by what? The number of dimensions in our balanced action, 5. It literally identifies this geometry, this simple geometric construction composed of those 5 rotations. With this simple geometric arrangement, we're defining the minimum possible volume complement, the hyperbolic figure 8 knot, the smallest way of subdividing the world. And that smallest subdivision externally defines a domain that partitions exactly in the way that defines the n hypersphere of maximal volume. What could be more tantalizing than a construction that defines the minimal volume partitioning, the smallest thing you can create that's then self-perpetual? That volume, that partitioned volume element, externally defines another geometric form of limiting value. But instead of being the minimum possible volume partition, this defines the maximal volume partition. n hypersphere. So out of all the possible dimensions you could select for the n hypersphere in order to increase its volume, the maximal possible volume defines the counter construction of the minimum possible volume complement of the hyperbolic figure-8 knot. Alright, so with this construction, let's now take a closer look at the mass boundary, which has been minimally arranged into the mass of the electron. We can now try to look at the orthogonal directions or expressions of this balance. Not the way that this balance is being held together where we're riding the balance line, but instead look at orthogonal directions of the balance line where this thing is splitting maximally. Any squarely balanced periodic hyperbolic space has a total of 17 possible tessellations or tilings because there are exactly 17 plane symmetry groups. To find all of the possible tessellations of the Planck mass boundary, we orthogonally extend its trivial tessellation, the mass of the electron, under ideal balance of square splitting and joining, guaranteeing that three things, and these are all things we already now know about from our construction, we're just trying to be explicit about them. One, the Planck charge and the Planck mass boundaries partition under hyperbolic vortex connection, right? So our partition parameters are going to be J1, J2, and so on and so on. Two, the balance of that connection squarely hyperbolically bifurcates. So because we're explaining a vortex, if something's coming out of the throat of a vortex, it's coming out in a way that's radial, which means it's splitting in one way, but it's splitting in another orthogonal way also. And this is going to be an ideal splitting situation, so we're defining these splits as being orthogonal, but otherwise indistinguishable. Since we want it to be a split, the natural split, we're going to use the splitting parameter in geometry, the alpha Feigenbaum constant, of course, and we want it to be a hyperbolic split, so -1. And since we want it to be more orthogonal, but otherwise indistinguishable, of course, we'll just square this arrangement. This is our ideal hyperbolic splitting square arrangement. Third condition is that this whole arrangement is dilogarithmically persisting under unitary hyperbolic circular closed balance. So we mean it's being logarithmically braided under the +2/3 and the -1/3 divisions, okay, the internal split action of the hyperbolic figure-8 knot, but also this logarithmic braid means that we're going to have our dilogarithmic zeros. We're going to have both 0, 0 and our non-trivial 0 of the logarithmic integral. And we're also going to have the Euler-Mascheroni constant playing a central logarithmic role in our braiding. The tessellations that capture this precise balance of orthogonal square splitting and joining define the proton mass and the neutron mass, the way the Planck mass boundary, the thing that defines the dimension of mass itself, arranges into the electron balance arrangement, the geometric expression that singles out the mass value of the electron, and the way that balance falls apart and falls together geometrically expresses that boundary in two orthogonal ways that perfectly select out the mass of the proton and the mass of the neutron. Such a beautiful, beautiful prescription, but also such a precise description of reality. The action of the hyperbolic figure-8 knot externally fibers under two orthogonal circular actions, right? It splits into two different circular actions externally. And the product space of these two actions defines the asymmetric Clifford torus. Okay, asymmetric because they're different scale and size. The circles are not the same size. And this defines the orthogonal intersection of two squarely arranged circle splittings and one joining of circles. If we try to just draw a simple torus here, we can slice up the torus to show how the torus itself is in three different planes, defining two circle splittings and one circle joining, or one joining of two circles and two splittings of two circles. This one geometric balance maintains all of those actions at once. Okay, a simple cartoon thing to keep in mind, but it's generally helpful to remember that geometrically we're talking about a closed boundary that's toroidal. It's the asymmetric Clifford torus. The internal construction of this balance also extends to set the possible tessellations of all the allowed 17 fundamental values of mass. Mirroring the division structure of the hyperbolic figure-8 knot's internal complement volume, which is composed of 6 circles with an inside circle, so 7 circles in its most general decomposition. That construction on the inside, when you look closer, it's got this whole figure-8 twisting in there, right? That central figure-8, then, if we add in all of it, we're splitting things and then squarely splitting and squarely. So we're adding more and more splits as we go and closing out the system. So as we split and twist, everything's closed. So our construction here, if we go from outside to inside, is a system made of 6 circles and then 1 circle and then a thing that's split in half and then it's split in half in another way and then another way as we go. What's the single thing represent? The single thing represents our joining map of the mass boundary, the arrangement between the neutron and the proton and the electron. Under this constructive arrangement, the joining map of these 3 trivial tessellations, the mass of the electron, proton, and the neutron, that define how the mass boundary itself, the Planck mass boundary, is constructively set, how it's balanced, how it's falling apart, and how it's falling together. Those 3 different expressions of the mass boundary extend, just like the charge boundary internally extended by the division structure of the hyperbolic figure-8 knot. Well, this mass boundary arrangement is also arranged under closed extensions determined by the internal construction of the hyperbolic figure-8 knot. Under that constructive arrangement, this balance naturally extends into a balance of externally phased and internally folded tessellations. And the orthogonally connected splitting map that's there at the same time, it extends into a balance of twists, splits, and flips. It's a purely geometric constructive arrangement we're talking about here, right? But both of these orthogonal extensions, both the extension of the joining map and the splitting map, define all of the 17 mass tilings. They select them all. All right, so we have the external phases, which extend to our trivial joining map into 3 different groupings, which happen to select perfectly the mass of the Higgs, the Z boson, and the W boson, and the mass of the down and up quarks. Notice again here the mass of the electron shows up in double roll. It's playing 2 roles in this construction. Important. Okay, internally, instead of arranging under these 3 different phase expressions, it's arranging the same balance under the internal fold expression. Remember, it's squared, 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 and squared, squared. So that internal constructive arrangement is showing up here. This construction selects the values of the charm mass, the strange mass, the muon mass, the tau mass, and our truth quark mass, and the beauty quark mass, and so on. Conversely, we can take this splitting map between the electron and the proton, this square splitting map of the electron proton, and extend it under what? Under adjustment of twists. How many twists are we talking? All right, division twists. So we have 2/3. So we have a 2/3 that's cubed. We have a 2/3 that's squared. That's our trivial construction. And we have a 2/3 to the first power. Notice what we're talking about when we're talking about the masses now. These masses are the singlet pieces, so the individual expressions of this braided balance. What braided balance? The braided balance of the mass boundary, the Planck mass boundary, the one and only mass boundary. The limiting expression of the dimension of mass is a deranged balance that partitions very specifically into this braided form. And the braids, or the individual expressions of that arrangement, are all uniquely selected by this geometric complete set of closed actions. So far, what we're saying is that we have defined the division properties of the simplest possible geometry. And the external parts of that geometry divide up and take on the geometric expression that perfectly defines both the charge of the electron, which internally divides exactly as the internal divisions are allowed, and the mass boundary wraps exactly into the mass of the electron and expresses itself orthogonally as the mass of the neutron and the proton. And the way that that arrangement, that simplest possible arrangement, extends under symmetry of the internal construction, defines all the rest of the mass particles in the entire set. The full set of mass particles that define the constructive parameters of mass in physical reality. Literally every building block of mass from which anything in reality could ever be constructed that we've ever found in any way, all of them are perfectly projected as the tilings of this division balance, the one that defines the mass boundary, the Planck mass boundary, under simplest external expression of the hyperbolic figure-8 knot. This means that we now have a list of partition parameters that define this simplest universe. So here's our list of partition parameters of the hyperbolic figure-8 knot. Obviously our red n equals 5, that's important, and our blue b is equal to 7. But we have these elementary partitions that are rotations, these are geometric rotation constants, right? The 0th external rotation constant, the first external rotation, all the way to the 4th external rotation constant. These numbers are intrinsically prescribing the minimal possible geometric balance, the hyperbolic figure-8 knots decomposition structure. So these numbers are central and critical, so we're listing them here as part of our partition parameters right from the beginning, and we can define the boundaries of the actions themselves, of the dimensions of this balance, as, well, it turns out they define perfectly the Planck time, the Planck length, Planck charge, Planck mass, and Planck temperature, as literally the dimensions of our physical reality. So we've now constructively defined the boundary conditions of the minimal possible universe, and those boundary conditions define as one complete set at the same time boundaries that together close against each other but keep each other going, and those boundaries, all 5 of them, select out the 5 unique Planck constants, literally defining the boundaries of the physical world we live in. The Giesking constant, of course, now becomes a central geometric parameter of our construction in the figure-8 knot complement volume, of course, and the difference between those is a multiple of 2, remember. Euler's number, obviously very central. We're going to get to this in part 3 of this video. But in this chapter, let's just take for now that Euler's number is a central constructive parameter of our geometry, and as is Archimedes' constant, or pi. But also we have these new hyperbolic vortex partition constants, right? The J1, J2, J3, J4, or Jr and J theta. Then we have central numbers in all of math, the alpha Feigenbaum constant, the delta Feigenbaum constant, the Euler-Mascheroni constant, the non-trivial 0 of the logarithmic integral, right? Because we have this dilogarithmic balance centrally written into our construction. Gauss's constant is built into the hyperbolic limits. The lemniscate constant, or the first lemniscate constant, and the second lemniscate constant are constructive parameters of our division, right? We saw how on the Planck charge boundary, this is how the balance is being maintained. The Dotty number means that you're going to have a fixed point. This cosine fixed point is the Dotty number. We have the omega 1 constant and the omega 2 constant, the special periods that's maintaining the harmonic division balance of this construction. The universal parabolic constant, the Weierstrass constant, doubly periodic parameter. We have the dimension at which the n hypersphere has maximal area, and we have another geometric constant that defines the dimension in which the n hypersphere has maximal volume. Also, now, we can add the 17 tessellations of the Planck mass boundary as intrinsic geometric parameters of this construction, right? So our simplest possible geometric balance that projects this mass boundary, we know it so well now, we can tell you all the ways, because of how it's breaking up repetitiously over and over, maintaining a balance as it does, all of the tilings, the unique individual expressions of that balance are now intrinsic properties of the system. And here we list them all. They define the electron mass, proton mass, neutron mass, charm quark mass, down quark mass, up quark mass, and so on and so on and so on. Notice that all the black digits in this list needed to be explained. They were measured values that we had with extreme confidence. Okay, starting at the green is where we didn't know them for sure. So all the green values, all the green digits are extensions of predictions. So all the red values in this list are the ones that have a discrepancy between the prediction and the measurement. Notice there are no red digits. Every single prediction of the mass values we've measured for the fundamental parameters of mass in our physical reality are perfectly prescribed. All of them. We got a single geometric prediction of a closed single system balancing one single boundary. Understanding what each of these mass values actually are means that ultimately we now have access to the action of each of them uniquely. We can now try to take advantage of the action that each of these uniquely represents. I mean, that's a really nice advantage of reality. Right now we take advantage of the actions of electrons quite a lot. We found many ways to do this, but we're not really taking advantage of the action of up quarks and Higgs bosons on purpose well currently. Of course, chemistry does this as a consequence, but we didn't have a model that explained exactly how to, well, certainly not how to individually take advantage of any of these actions, right? Just as under certain collections and transformations we could. All right, so far now, in this entire chapter, we've arranged just the balance map and the splitting map and the joining map and the extensions of those simple three constructive maps to define all the tessellations of the Planck mass boundary. Literally one simple arrangement of the mass dimension itself, the boundary of mass itself. That one geometric arrangement, we've defined all of its possible tessellations, all the parts that are maintained in this balance. And all those parts, they've selected the values of mass that define the 17 fundamental particles of matter in physical reality. What a beautiful, beautiful, beautiful extension so far. We've got the charge boundary defining the charge partitions that show up in reality and the constructive arrangements between all the available ones. We have the mass boundary perfectly and ideally arranging itself into the mass of the electron, and that construction is tearing itself apart in two orthogonal ways, in square division or a splitting map, and that splitting is also in another orthogonal way coming together because the whole thing's closed. So we have a balanced expression that gives us the mass of the electron of one boundary. Of the same boundary, we have an expression of how it's squarely tearing apart, a completely different expression, but of the same boundary. So it's still of mass, and that expression defines exactly the mass of the proton. And orthogonally, we have the square splittings come together to form the mass expression we call the mass of the neutron. All three of these are tied together in the minimum possible balanced expression of the one boundary, the one geometric balanced action that we're labeling as the dimension limit of mass itself. The thing that defines the dimension of mass itself is this boundary. It's a very deep, deep grip into what's going on, right? We have a very visceral picture developing now of the balance and the division balance properties that are constructively just maintaining the minimal possible geometric construction. We've now defined how the inside of that form, of that internal boundary, the charge boundary, has partitions, and how the mass boundary partitions. But remember, the charge boundary and mass boundary have a connection between them. There's a whole continuous description going on there. So we know how now we lump it up as this twisting about goes on. We know how the individual tessellations must be, but we know that from extending the pattern, right? We got the values so far by extending the splitting and the joining maps, by extending those and finding what values must fit. Well, we can also ask now, what are the unique geometric expressions of each of those individual tilings, or tessellations? Chapter 9, Individual Tessellations. Every unique tessellation of the mass boundary represents a fundamental geometric tiling from which the hyperbolic figure-8 knot's external mass boundary can be periodically constructed. These tilings are either geometrically combinatorial, defining a balance between two actions, the second of which ends on the termination boundary every time, or primitive, so referencing a single division action. Or you can think of primitive ones being ones that have a terminal action of 0. That's what I mean. So let's examine, and that's going to exhaust every possible option here. And in fact, you would think that most of them are going to have some terminal actions we've seen so far, right? Most of them are just division properties, so they have a terminal value of 0. Now that we have the values of the individual mass tessellations, we can easily check to see what geometric role that tessellation is playing. That is, we can plug in the number we now have for the mass of the charm quark into a simple comparative construction using only our hyperbolic vortex partition parameters as our search space, and find the geometric parameter that defines that construction. So in this case, we take the mass of the electron and we divide it by the mass of the charm quark. And then we multiply that arrangement by the second hyperbolic vortex partition constant squared over the first hyperbolic vortex partition constant squared. And real quick, before we get to the next part there, the first hyperbolic vortex constant squared happens to define the fine structure constant. So the second hyperbolic vortex partition constant squared is a sister to the fine structure constant. So really, we have the second fine structure constant divided by the first fine structure constant here. And what does this square arrangement get us? It selects the dotty number, the unique real fixed point of the cosine function. And this is a universal attracting point, a special point for the cosine function. Under the same constructive arrangement, but now putting the down quark in place of the charm quark, and the power of the first of J1 is raised to the 0th power, just not in this role, we find that arrangement simply selects the non-trivial 0 of the logarithmic integral. Think about what this means. It means we're the mass expression of the electron divided by, so made up from tiles of the down quark multiplied by the second fine structure constant is equal to the non-trivial 0 of the logarithmic integral. To tile the electron mass from the up quark mass ends up being 2 divided by the omega 2 constant to the 5th power to all 5 rotations. The strange quark mass tiles the electron mass via the Khinchin harmonic mean. The bottom quark mass prescribed here with the first lemniscate constant, and the top quark mass is prescribed with the second lemniscate constant. The Higgs mass tiles the electron under division of the first root of the Bessel function, but to the 7th power, to the power of the break and scale symmetry of our system. The Z boson mass employs the Laplace limit, which is defined by the hyperbolic sign of the real fixed point of the hyperbolic cotangent, literally the limit of this hyperbolic construction, to the 5th power. The W boson mass, very interestingly, depends on the first non-trivial root of the zeta function as its geometric bound. It selects the first non-trivial root of the zeta function, which up until now, as far as I am aware, has had no simple connection to any geometry that's understood. Continuing down the list, we see the tau mass and its geometric construction depending on the hyperbolic figure-8 knots volume, and the hyperbolic secant of the tangent of 1/2, the base hyperbolic split of the hyperbolic secant of the tangent of 1/2 on the terminal boundary. all of this construction is talking about the elementary hyperbolic balance arrangement under a square split division arrangement. The muon mass and the tau neutrino mass and the muon neutrino mass and lepton neutrino mass. Chapter 10, Constants of Nature. So far, we have found that the balance of the hyperbolic figure 8 knot is responsible for the persistent arena of reality, minimally decomposing into 5 unique actions: time, space, charge, mass, and temperature, with sharply defined boundaries, the Planck constants. And that the external domain of that balance connects via the hyperbolic vortex equation, which partitions the Planck charge and Planck mass boundaries into the exact charge and mass values that define the fundamental particles of matter. In this chapter, we discover that every unique balance of boundaries maintaining this minimum geometry defines a constant of nature. To unveil the geometry of each constant of nature, we think of them as binomial combinations of a primary partition action, which we'll represent as A sub p, on a primary intersection of boundaries, so B sub p, and a terminal partition action, A sub t, on the terminal boundary intersection, which we represent with this box symbol. Let's say that again. To unveil the geometry of each constant of nature, any one you want to pick at all, you just think of it as a binomial combination of a primary partition action on a primary intersection of boundaries. So it's a primary partition action applied to an intersection of boundaries, and a terminal partition action on the terminal boundary intersection, the fixed one. So all the different possible expressions on the primary boundary need to be found, but all the terminal boundaries are always this box, okay? So we need to find 2 different unique actions, partition actions, and we need to find the unique boundaries for the primary boundary assortment in each case, and that'll allow us to fully explain each concept of nature. Since the terminal action doesn't come into play until the 7th digit, this equation can be solved in pieces. It's always important to remember this. When we have this universal binomial factorization prescription, this constructive way of arranging the world internally and externally, and the division between the internal and external means we have a terminal boundary that's 7 powers smaller in its contribution than the primary boundary. That means we can safely ignore the terminal contribution of this balance at first, right? And solve for its primary action and primary boundary. So just worry about those 2. And then once we find the primary action, primary boundary, we can return to the full equation and solve for the terminal action. Step 1 is to temporarily set our terminal action equal to 0. We're going to ignore that whole right-hand part, okay? And then whatever constant of nature we're trying to geometrically interpret, we're going to construct its primary boundary from the dimensions of the constant in terms of the natural partitions we have defined so far. So the boundary of time and length and charge, mass and temperature, or the mass of the electron or the proton. So composed from these natural division boundaries. Step 2, if the primary action, so once we solve for the primary boundaries, if the value we have isn't already correct for the first 7-ish significant digits, then if it is correct, then the primary action is going to be just 1. If it's not, then you still have to solve for the primary action that's being applied to this. It's not just a unitary balance you're talking about between these boundaries. There's some element that's not unitary. There's some sort of other geometric part playing a role, and you need to solve for what it is. And that other part has to be constructively composed, of course, of the figure 8 knots partition parameters. So we have a list so far of those parameters, so you can go look at those lists and then simply solve. Find the simplest geometric description of what's going on using those parameters. Then step 3, once we've solved for both the primary action and the balance of primary boundaries, then we put those values back into the universal binomial factorization prescription and solve for the terminal geometric action of this constant of nature, so our A sub t. So we're going to have 2 examples, and this process applies to every single constant of nature. First, the speed of light. We look up its measured value. It's listed at 2.9979248 times 10 to the 8 meters per second. Okay, so we have the value for the speed of light, the measured, defined in this case, value of this constant of nature. How do we interpret what it geometrically means? First, we need to find the primary boundary intersection and the primary action, right? So to find the primary boundary intersection of any constant of nature, we look at its balance of dimensions. So we just look at the dimensions in the constant of nature. The dimensions that the constant of nature is defining a relationship between, to begin with, right? If you ask, what is the speed of light? It's 2.9979248 times 10 to the 8 meters per second. That's the answer of what it is. It's a number of meters per second. It's literally a dimensional relationship. So for the speed of light, since it has the dimensions of meters per second, its primary boundary is going to be equal to the natural boundary of length, or the Planck length, divided by the natural boundary of time, the Planck time. So we set our primary boundary intersection equal to the Planck length divided by the Planck time. And this gives us a value of 2.9979256287110 times 10 to the 8 meters per second. Extremely close to the value we need, at least for the first 7-ish significant digits, right? Since this number already yields the measured value of the speed of light, well, up to the first 7 significant digits, we know that for this constant, the primary action has a value of 1. So to finish, we now plug in our primary action and primary boundaries back into the universal binomial factorization prescription and solve for the terminal action of the speed of light. Therefore, the speed of light is going to be equal to the Planck length divided by the Planck time and some terminal action on that terminal boundary. So solving for the terminal action now, we find that it's equal to negative 3/2 of the first root of the Bessel function. The quantized Hall conductance. The value of the quantized Hall conductance is 3.87404614 plus or minus 17 in the 14. So it's a sharply known number, right? Times 10 to the negative 5, and its dimensions are seconds times coulombs squared over meters squared kilograms. That means dimensions of time and charge squared over dimensions of length squared and mass. Following the same procedure for the quantized Hall conductance, we ignore its terminal contribution and match the dimensions of this constant to its appropriate Planck boundaries. Since its dimensions are seconds coulombs squared divided by meters squared kilograms, we set its primary boundary equal to the Planck time multiplied by the Planck charge squared divided by the Planck length squared and the Planck mass. Next, we solve for the primary action in terms of the hyperbolic figure 8 knots partition parameters. In this case, it's not equal to 1, so we search for its value in terms of the hyperbolic figure 8 knots partition parameters. The primary partition action is equal to J1 squared over 2 pi, and J1 squared is equal to the fine structure constant. Then to finish up, we plug in the primary partition action and the primary boundary intersections back into the universal binomial factorization prescription and solve for the terminal partition action of this balance, which ends up being simply the second partition constant of the hyperbolic vortex. In general, therefore, we're saying there's a balance template because of the division structure of this minimum geometric construction. There's a balance template. It instructively informs us of the 2-part players in each balance. In every balance, there's a primary boundary and a terminal boundary. And these are intersections of boundaries. And the terminal intersection of boundaries is a fixed set. It's just the Planck length times the Planck mass over the Planck charge squared. That's the termination boundary, divides between the arrangement on the inside and the arrangement on the outside. The primary boundaries will be different in each case. The terminal actions will be different in each case for every constant of nature, but the terminal boundaries will always be the same. And the primary boundaries are determined by the dimensions of the constant. And the primary action then is just determined by the geometry that maintains that dimensional arrangement. And the terminal action represents the geometric partitioning that's being maintained on the terminal boundary. The big highlight note here is that this universal binomial factorization prescription allows us to identify the constructive geometry of every constant of nature. It allows each and every one of us to individually discover and confirm the geometric arrangement that defines each constant of nature. Note that 1 mole combines the dimensions of the Planck charge and the Planck mass. Revealing the constants of nature by using the universal binomial prescription above, we find that the fine structure constant, the first and most exciting geometric number to find an explanation for, the number that's dimensionless and known to be written centrally into the constructive parameters of existence. It is a central constructive parameter of existence. It's centrally scripting the division structure of reality. It's centrally in there, and it plays an important role just as much as pi plays an important geometric role. And yet there's been no story whatsoever shedding light of what this number is, where it comes from, why it's embedded into nature. We've had no geometric story making sense of this number, which is why it's stood as the central identified mystery of reality that physics has uncovered, the one that we know carries the most insight if we had this story there, right? And yet there's been no story. There's been no partial story that's made any sense of it. Here, the fine structure constant is literally just the first partition constant of the hyperbolic vortex squared. It means we have a square vortex minimally partitioning. That intersection is the fine structure constant. So the fine structure constant, how many significant digits? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 significant digits. It's an extremely well-known number with no explanation whatsoever. And here we've gotten a geometric explanation that's centrally scripted into our minimal construction. The elementary charge, or the charge of the electron, is equal to G1 times the Planck charge. The first hyperbolic vortex partition parameter multiplied by the Planck charge boundary gives us the value of the electron charge. And look at the precision. It's a beautiful, beautiful, simple explanation. The Compton wavelength is equal to 2 pi times the Planck length and the Planck mass over the electron mass. A circular relationship between the Planck length and the Planck mass divided by the electron mass. And the terminal action is equal to the alpha Feigenbaum constant and our break and scale symmetry divided by 2. You can think of this as a collection of 3 division parameters, 1/2, b, and alpha Feigenbaum. And they're all centrally part of our geometric divisions. The Josephson constant is equal to G1 over pi, that's its primary action, and its intersection of boundaries are the Planck time and the Planck charge divided by the Planck length squared and the Planck mass. The terminal action of this balance is equal to 2 things. One, like above, b over 2. But the other is e to the 2 gamma, where lowercase gamma here is equal to the Euler-Mascheroni constant, divided by the imaginary part of the omega-1 constant cubed. So you asked Wolfram alpha to solve for what the value of the terminal action must be, and it said that it was e to the 2 gamma over the imaginary part of omega-1 cubed times by 7 over 2. E to the 2 gamma showed up before as our split coefficient, right? Our braiding split coefficient along the mass boundary. And the omega-1 constant, remember that one showing up before? I think it was in chapter 4, part of the equine harmonic half periods associated with the gamma function, the Lemniscate constant, and the Weierstrass constant. Let's go further to look at the other clues we get from the constructive balances of the remaining constants of nature. Planck's constant is equal to, well, its primary action is just unitary, it's a 1. Its primary boundary intersections are the Planck length squared times by the Planck mass divided by the Planck time. What's the terminal action? The terminal action is the square root of b times pi, or 7 times pi, divided by Apries constant, centrally connected to the zeta function and the gamma function and so on. The electric constant and Coulomb constant. If we look at these as a pair together, we notice that their boundaries, their primary intersection of boundaries, are composed of the same elements, but those elements are arranged under inverse association. In the electric constant's case, the Planck times squared is up top, and in the Coulomb's constant, the Planck times squared is in the bottom. And so goes for everything else. So the boundaries are inversely arranged, but the primary action has a unitary to spherical arrangement. In the first case, it's 1 over 4 pi. In the second case, it's just 1. The terminal actions, on the other hand, have an inversion that is different. Instead of inverting the numerators and denominators, this inverts the sign only. The terminal actions of both these constants are identical, except for sign. Quantized Hall conductance, as we saw earlier, has the fine structure constant divided by 2 pi as its primary action, and its terminal action is just the second hyperbolic vortex partition constant. The Bohr magneton has as its primary action G1 over 2, and its terminal action 2 over G2 times pi squared. The magnetic constant is a very unique mirrored constant in that this constant has as its primary boundary and its terminal boundary the same boundary. It's an alignment, so we got a mirrored inversion going here. And in one case, we're talking about a sphere, 4 pi is its primary action. And in the terminal case, there's 3 division parameters at play. The second partition constant of the hyperbolic vortex, e to the gamma, and the square root of 3/2, where gamma is the Euler-Maccheroni constant again. The first radiation constant, in this case the primary action is 4 pi squared, and the terminal action is G2 squared times 2 gamma minus 1. 2 gamma splits minus 1 make it hyperbolic, but multiply that union by the second hyperbolic vortex partition constant squared. The electron Thomas cross-section has something similar to the first radiation constant in that its primary action also has a 4 pi in it, right? And its terminal action also has the G2 squared times by, this time, the lemniscate constant instead of 2 gamma minus 1. The conductance quantum has a primary action of the fine structure constant over pi, and a terminal action of the second fine structure constant over the non-trivial zero of the logarithmic integral cubed. In the Bohr electron radius, the primary action setting the electron radius is, of course, G1 squared. The terminal action is G2 squared times by the square root of 6 over the imaginary part of the first non-trivial root of the zeta function. The atomic mass constant here is selected by the Giesking constant, the first and second hyperbolic vortex partition constants, and terminally determined by the hyperbolic vortex radius constant and a hyperbolic sine of the cosecant of 4/3 n. The characteristic impedance has a primary action that defines a sphere, 4 pi, and a terminal action that's 2n squared over b times by the gamma of x min to the 4th power, where gamma of x min defines the minimal positive argument value of the gamma function. So it's a special point in the gamma function. You have the gamma function landscape, and that's the special point of the gamma function. The Stefan-Boltzmann constant has a primary action of zeta of 2. Before we had a zeta of 3 playing a role, which was Apries constant. Here it's zeta of 2 divided by 2n. And the terminal action is the universal parabolic constant over 2 times J1 all squared. Avogadro's constant, the boundaries are here 1 over the Planck charge times by the Planck mass. Okay, the Planck charge and Planck mass are both in the denominator together, and that defines that collection, a mole. When you put those two together, you can call that a mole. And then when we ask what is the primary action of this single mole arrangement, we get 6 J1 squared, which again is the fine structure constant, over e to the gamma. So there's a splitting coefficient division programmed right here that defines the Avogadro constant. The terminal action of this balance is 2J2 times by the universal parabolic constant, all squared. The von Klitzing constant, this is one of the most beautiful ones. This constant of nature has a primary action of 2 pi divided by the fine structure constant, or J1 squared. Its terminal action, 1/2 something r squared, a very familiar sounding relationship in physics, right? But that something is the real part of the infinite power tower of the imaginary root, or of I. 1/2 times the real part of the infinite power tower of I times the hyperbolic vortex radius squared. This is the terminal boundary arrangement of this constant, whose primary boundary arrangement is a circle divided by the fine structure constant, or a J1 squared. So we're adopting the trivial unitary subdivision, this power tower splitting action, as the action that keeps the connection here. Beautiful. The Hartree energy has a primary action of J1 to the 4th power, so that would be the fine structure constant squared, and its terminal action has the omega-2 constant to the 4th power in it. The speed of light we've gone through before. The spectral radiance constant has something similar to the speed of light in the terminal action. That is, instead of being 3/2 times the first root of the Bessel function, the terminal action of the spectral radiance constant is the square root of 3/2 times the first root of the Bessel function. The classical electron radius has a primary action of J1 squared, again, and a terminal action composed of more parts, n times the alpha Feigenbaum minus 1, and we have 2/3 again, and the volume of the hyperbolic figure 8 naught, both to the 1/2 power. The nuclear magneton has a primary action of J1 over 2, and its terminal action is Jr squared times 2/3, and the volume of the hyperbolic figure 8 naught divided by n, or 5. The second radiation constant has a primary action of 2 pi, a circle, and a terminal action of 3 constructive parts, 2n, so a double cover, e to the 2 gamma again, and the real fixed point of the hyperbolic cotangent squared. We've seen all those constructive parts before. The mu on g factor is equal to -1/4 times the alpha Feigenbaum minus 1 construction, multiplied by the square root of the volume of the hyperbolic figure 8 naught to the 7th power over 5. And the terminal action is 1 over 7 and the square root of n over b, so 5 over 7. The electron g factor has a primary action that's identical to the primary action of the muon g factor, and its primary boundary is just 1, just like the muon g factor's primary boundary is. Its terminal action is a combination of J2s and J1s and the Frenz and Robinson constant. The molar gas constant has the same primary action as Avogadro's constant, and its terminal action is 18n times the square root of b over GGI, Giesking's constant for the minimum 3 manifold. Recall that 18 is the number of derangements for balance 2 in the minimal geometric universe. The magnetic flux constant has a primary action of pi over J1, and a terminal action of 8 times the Gompertz constant. The quantum of circulation has a primary action of pi, and a terminal action of 8 times Cahane's constant. This is another thing now going into prime number construction. Proton G factor has a primary action of the second hyperbolic vortex partition constant times by 2 times Mertens constant plus 1. And its terminal action depends again on the Cahane's constant. Mertens constant, by the way, also related to prime construction. Rydberg constant has a primary action of J1 to the 4th over 4 pi, and a terminal action of negative 4 second lemniscate constant and b to the 2/3. In the proton gyromagnetic ratio, the primary action is composed of the square root of 3, e to the gamma, our braiding coefficient, and Jr over J1 squared. Its terminal action is n times the square of 3 times the imaginary part of J3, multiplied by the cube of the delta Feigenbaum constant over b, 7. The neutron magnetic moment compares the derangements of the 5 fundamental actions to the gamma value of those 5 actions. Faraday's constant ends up being equal to Avogadro's number multiplied by J1 and the Planck charge boundary, which, if you remember, J1 and the Planck charge boundary equals the electron charge. So Faraday's constant equals an Avogadro's number of electron charges as its primary action. Its terminal action is Jr squared over 2 pi times by n over the derangements of n. It's beautiful. It's absolutely beautiful. The neutron G factor isn't too shabby itself. It's just the gamma function as its terminal action. And gravitational coupling is the ratio between the mass of the electron and the Planck mass, squared. So take the ratio, square the ratio, that's the gravitational coupling constant. It's a dimensionless constant also. Okay. Compton angular frequency has a primary action of 1, it's unitary, and its terminal action is 1/2 gamma n. The Schwinger magnetic induction has a primary action of 1 over J1, and a terminal action of negative 2 pi times 3 times the imaginary part of the infinite power tower of I squared. The gravitational constant, another beautifully, simply captured form here, has a primary action of 1 and a terminal action of negative 1/2 pi Jr squared times the gamma function value of n rotations. The Boltzmann constant has a primary action of 1. Its terminal action is the square of 1/2 pi Jr squared. The classical electron radius divided by the proton radius equals the lemniscate constant times by the square root of 3/2. The most mysterious parameters in existence are no longer the parameters of existence. The simplest possible partition balance is responsible for all the action parameters of quantum field theory and general relativity. This minimal balance persistently maintains the 5 Planck boundaries, and the connections between these boundaries trivially define the 4 fundamental actions of nature: the strong force, the weak force, the electromagnetic force, and gravity. Think about it. This construction not only picks the partition parameters of reality, but aligns them so that their interactions define the forces of nature. The strength of the gravitational force is determined by the ratio of the Planck length cubed to the Planck time squared and the Planck mass, terminally arranged under trivial spherical factorization. And the strength of the electromagnetic force compared to the strong nuclear force is equal to the first hyperbolic vortex partition constant squared, which defines the fine structure constant. And if we square that ratio again, we get the ratio of the classic electron radius compared to the Bohr electron radius, which is J1 to the 4th power. And the radius of the helium atom and the lithium atom and so on are then tracked as the ratios go out of A0 over 2 and A0 over 3, where A0 is the Bohr electron radius. The non-relativistic ground state wave function of the hydrogen atom So the ideal atomic construction is defined as being a naught to the negative 3/2 power divided by gamma of 1/2 times by e to the negative r over a naught, where r is our radius. So now we have a bunch of numbers that can be added to our constructive parameters of reality, our list of numbers that belong to the construction maintained by this minimal division balance. The fine structure constant, the electron charge, the Compton wavelength, and so on down the list. We know all these numbers now, not just to the black digits, but we can extend them now geometrically all the way out and include all these green digits. Since first publishing these geometric explanations of the constants in nature, one of those constants, the magnetic moment of the muon, called the muon G factor, has been measured to greater accuracy. This latest Fermilab measurement officially puts the number standard model theorists have been using for the muon G factor at 4.2 standard deviations outside the measured confidence interval, while the number predicted by the division parameters of the hyperbolic figure-8 knot lies inside the new experimental average. So far, we have discovered that the simplest constructible theory of balanced derangements, based on the minimal geometry of the hyperbolic figure-8 knot, defines an arena projected under 5 perpetual actions: time, space, charge, mass, and temperature, with Planck constant boundaries. The external charge and mass boundaries of that balance partition into the exact charge and mass values that define the fundamental particles of matter, and every intersection maintained by this minimal balance of boundaries defines a constant of nature. In other words, the partition parameters of the simplest possible self-balanced geometry precisely define the constructive parameters of physical reality, those of quantum field theory and general relativity. In the next video, we discover that the Planck union is duly hyperbolic, and that the story of this minimal derangement theory, this theory of everything, can also be told in terms of the gamma function and the Riemann zeta function.